Is this font size readable to everyone? Thumbs up. Are you? I think yeah, we got thumbs up. Nobody wanted to admit a thumbs down. Think about the same. Got 1 minute. We'll hang out here for just 1 more minute. Oh, yeah. So there's no need for any of you to log into anything. Following along is probably futile. So there I've already broken my promise that you'll have no doubts that it's easy to run when I say that. But yeah, I hope I don't disappoint everyone too much. Wait 1 more minute. Okay, let's go ahead and get started. So the idea here is to talk about running regional simulations with MPAS. And I have to admit that maybe I hadn't calculated properly when we put this together. We had originally thought that maybe the people who might be most interested in attending this session certainly would be familiar with running regional WRF simulations. And maybe they'd have some experience with MPAS, at least basic familiarity. But talking with people during the breaks and over lunches this week, I realized, maybe that might not have been the correct assessment of the situation. But I think that's okay. In the next couple of slides, number one, to prove to you that I know how to make QR codes as well, but also to give you links to more of the full, complete tutorial information. I think the things that we're going to be talking about this morning are somewhat complementary. So you'll have links to the formal material, but then seeing someone actually running programs and to say, all right, that's kind of what it looks like when someone who reasonably knows what they're doing is running regional MPAS. Maybe those two things are complementary. So even if you're not familiar with running MPAS at all, I think I've convinced myself, and hopefully you'll be convinced that maybe that's all right. So as we said in the abstract for this, the focus really is on demonstrating. So as you probably inferred, we will be looking at a terminal screen quite a bit, but demonstrating that with a bit of practice, in my opinion, which is probably biased, running regional MPAS simulations can be at least as easy as running regional WRF simulations. So that's the idea. I just wanted to set your expectations a little bit lower. That way, hopefully, you'll be pleasantly surprised if not. So I said this, but now there's going to be more slides after this, but we're going to try to keep the number of slides to a minimum and mostly focus on actually running things, again, to give you a feel for what it looks like when you run simulations with regional MPAS, which is the same as global MPAS. So that's, maybe there's a couple of myths to dispel here. We've heard people talk about does the regional version of MPAS work well? And I think that use of the word version is maybe not quite correct. It's the same code base. And from the perspective of the solver, there's only one difference between a global simulation and a regional simulation. And that is, do we or do we not enforce lateral boundary conditions? But it's exactly the same solver. So this idea that it's the regional version of MPAS, I think is not the way that I would phrase it. But the second myth, in my opinion, is that running regional MPAS is difficult. I've heard this off and on for the last few years. They say, is it really ready? Should we really be using it? And I think absolutely yes. And I think after yesterday's discussion session, you'll trust that if I have a negative opinion of something, I'll share it. But in this case, there's no doubt that regional MPAS is absolutely solid. So the hope then is to convince you that it's not only solid, but it's easy to use. So to prove to you, yes, I also can make QR codes, which seem to be the cool thing. If you are completely new to MPAS or you want some more formal material, you can go to this link. And if you're old school like me, you just want a URL. So there it is. 2 years ago at this workshop virtually, we presented, I think, like close to 100 slides to introduce regional simulations with MPAS. So you can get that slide deck, and that provides a lot more information. It's like a 35 megabyte slide deck that will take you to, and I don't know why you would want that like on your phone, because I want the slides on my computer, but there it is. The other source of helpful material is probably the virtual tutorial, and the most up-to-date version is the tutorial from May of this year. So you can go to this URL to find that material. And that includes the full set of lecture slides that we presented over 3 days. So we're kind of condensing, everything that we talked about there by a factor of 16 into an hour and a half. So all right, so there's 8 easy steps. I had a different title slide, but I decided to try to be a little more serious this morning. But there are kind of 8 easy steps, in a sense, in the most general sense, to running a regional MPAS simulation. And the first one is somewhat different from what you would do with the WRF model. So in WRF, for real data simulations, you know that you can run this GeoGrid program, right? And it's easy to choose a map projection and to generate basically a 2D array of latitudes and longitudes and to interpolate fields to those geographic locations. And I'm sure probably all of you have heard at this point that generating certainly variable resolution MPAS meshes is quite an undertaking. So as yet, we don't really allow you to generate your own mesh. So as a consequence, you need to download a mesh. And there's a mesh download page where you can download quasi-uniform meshes and also variable resolution meshes. So that's the first step. I can also say that much like the geographical data sets that you probably download for WRF and that are also used by MPAS, if you know that you're going to be working with MPAS, why not just download all of the meshes, put them on a shared file system so that you can share them with all of your colleagues, and you've downloaded them once. They don't typically change, and if we do change something about them, we'll send out an announcement about that. So that's the first step. The second step, and this really only applies generally if you're running variable resolution regional simulations, is to take the mesh that you've downloaded and to rotate that region of refinement so that it's located over the part of the globe where you want refinement to be. And that's typically somewhere where you're running your regional simulation. I mean, I suppose in principle, you could rotate the high resolution outside of your area of interest, but why would you do that? And I said that this is typically done for variable resolution simulations. That being said, we have taken quasi-uniform meshes and rotated them to look for grid imprinting in idealized simulations. So, I tend to, I can't resist being pedantic sometimes, but more or less, you only want to rotate a mesh if it's variable resolution. So the idea is when you download the mesh, the refinement is over the origin at 0 degrees latitude, 0 degrees longitude, but you're running a simulation over Colorado, so you're going to rotate it to 39 degrees north and 105 degrees west longitude. So I should say here that the thing to keep in mind throughout these 8 easy steps before we actually demonstrate them is, ask yourself, does that make sense? Was there anything conceptually difficult there? And I hope the answer is no in all cases. And if that's not the case, please don't feel shy and ask a question. So we've downloaded a mesh. If it's variable resolution, we've probably rotated that area of refinement using a simple solid body rotation. As we'll see in just a few minutes, that takes all of 30 seconds to do. We're not changing the connectivity of any of the cells. We're just recalculating effectively the latitudes and longitudes of all of the cells. So that's easy. The next thing we want to do is to cut out some part of that global mesh. And that extraction is going to define basically our regional simulation mesh. And we have a tool for doing this that's fairly flexible, and we'll demonstrate that it is fairly easy to use. And it's very hackable. And I'll explain what I mean by that in just a few minutes. So that makes sense. We can take a global mesh, identify some region, take those cells and write them to a new netcdf file and call that our regional simulation domain. So that's pretty conceptually easy. Once we've done that, so far we just have a mesh. So we'd like, just as we do with GeoGrid, we'd like to interpolate terrain elevation, land use categories, soil categories, deep soil temperatures, climatological albedos, vegetation fractions, all of the things that GeoGrid does. We're doing the same thing with a program called the Init Atmosphere Model Program. After that, this is something that's familiar to anyone who's used WRF. We still use the ungrib component of the WPS to take grib files, presuming your first guess data set comes in grib format, and to write those to this intermediate file format. So nothing specific there, or nothing unique there. Then we, in principle, now that we've got a terrain elevation field, we want to generate a vertical grid. And in MPAS, probably most of you know that it's a kind of a smooth hybrid terrain following vertical coordinate. So we can't generate that vertical grid until after we have a terrain field. That's an easy operation. So we often combine it with the step of doing a three-dimensional interpolation of, can you see my cursor? You can, awesome. So we often combine that with the work of interpolating these intermediate fields onto that vertical grid. So this is kind of two logical steps, but one practical step. After we've done that, of course, we just interpolate some LBC files, and then we run MPAS. So that's the most general case. I say eight easy steps because I think there's nothing, again, conceptually difficult with any of those. And just for comparison, if you look at the steps to run a WRF simulation, you can say, well, that's only 5 steps there, right? If my counting is correct. So this is at least 60% more difficult than running WRF. But really, these first 4 steps are kind of the same thing that we're doing with the GeoGrid program, where we define regional domain or domains, interpolate static terrestrial fields. That's what we do with GeoGrid. But there's a lot that's going on in this single step in WRF. Good, the cursor doesn't show up on my screen, but it does there, right? So you're choosing map projections, you're choosing EWE and ESN values, you're making sure that for the nested domains, they're an integer multiple of the nesting ratio +1. There's all of these things that you forget about when you run WRF that you take for granted. And so I would say these first 4 steps here are in concept not much more difficult. I'll try to make an argument later that there's a good reason for breaking up this initial domain setup and static field preprocessing. It allows us to reconstitute those steps in different orders or to omit certain steps when it makes sense. And we'll demonstrate that over the course of the next 80 minutes or so. Ungrib is the same. And then these 2 steps are basically kind of a refactoring of these 2 steps for MPAS. The partitioning between the steps is a bit different. One thing is handled all by the Rio program and by the MetGrid program, but it's in concept nothing that you weren't already doing with WRF. So yeah, maybe more steps, but each step is really simple. So just to look at things a little bit differently. So I promise not too many slides, and then we're talking for like 15 minutes about slides, and we'll get to a terminal window here in just a minute. But just to look at this a little bit differently, because I think we can point out some interesting things. So mesh generation right now, again, is something that you can't do. We do that, and certainly we take requests for variable resolution meshes. But in principle, you would download a mesh. Maybe if I go to a laser pointer, that's better. If it's a variable resolution mesh, you might want to rotate it. If it's quasi-uniform mesh, you probably can skip this step. You can go on and interpolate static fields to the entire globe and then cut out a subsection of those static fields, and then move on to, we'll talk about this terrain blending step in just a couple of slides. Generate a vertical grid, interpolate initial conditions, lateral boundary conditions, and run the model. The interesting thing here, and this goes back to this remark that I made in the previous slide about being able to reorder those initial steps, we can do things in a different order, right? So rather than rotating a global grid and interpolating static fields to the entire globe before cutting out a subregion, we can actually first rotate the grid, cut out a region of the grid, and then interpolate static fields just to that subsection of the globe. And that's what we'll do when we set up and run a regional simulation here first. But then towards the end, we'll do like a speed run through another regional simulation where we'll do things in the opposite order, just to show the reasons why you might go one route or the other. But this is to illustrate that there are multiple pathways. And again, that sounds confusing maybe at first, but think about when you first learned how to run WRF, there was a lot of things that was confusing. So It's just a matter of familiarity, I think. So through those different pathways, this is kind of the general 8 steps if you're running a variable resolution simulation. If you're running a quasi-uniform regional simulation, the steps can be a bit different. You can't do this yet, but after we release the 8.0.1 bug fix, probably by next Friday, I will put available on the download page static files, mesh files that have terrain, land use, soil categories for all of the quasi-uniform meshes on the download page. So the steps now are only 6. So we're getting closer to what you would do for WRF, right? You download a static file, and because it's quasi-uniform, you don't need to rotate it. So why not just download the entire globe worth of terrain already on the mesh? You can cut out a subregion, and then the rest of the steps are the same. So that is an illustration of the value in being able to reorder steps. Maybe this slide just illustrates that if you happen to be already familiar with running global WRF simulator, global MPAS simulations, you already know most of the steps involved in running regional MPAS. So there are just a few additional things. This limited area tool that allows you to cut out subregions of either a mesh or a static file. This terrain blending step, we'll illustrate that with a few slides, is new. And then generation of lateral boundary conditions is new. But everything else is basically the same as running a regional simulation. Sorry, a global simulation. Sorry, this is about the time that I'm usually rolling out of bed, so I have to think a little more clearly here. So that's that. Lastly, looking at this flowchart, just in terms of repositories, it's a bit different from WRF. There are actually just 4 repositories that you need to download, and that'll be kind of our entry point to a terminal window. So the first thing is, as we said, you still need the WPS, but only for the ungrib component. And if any of you actually read the release notes for WRF or for the WPS, you'll know that it is easy to compile just ungrib these days. You can say configure --no WRF --build -grib2 -libs. And you can have the WPS compile Jasper and zlib and libpng for you, and you don't need to have compiled WRF first. So if you want just ungrib, that's really easy to do. There is an MPAS tools repository, as we'll see, that has this tool that can do solid body rotations of meshes. There's a separate repository right now that contains the tool that allows you to subset either meshes or static files. And given that this is basically just another tool, we do intend to merge this MPAS limited area functionality into the MPAS tools repository. So down the road, there will probably not be a separate repository for this. And then lastly, there's the MPAS model repository, which if you're at all familiar with MPAS, you know there are 2 what we call cores. So there's this program that is compiled from the init-atmosphere core called init-atmosphere model that handles all of these initialization steps. And then there's a core called the atmosphere core that, when compiled, gives you the atmosphere model program, which is like WRF.exe. So this is kind of like GeoGrid, MetGrid, and Real all combined into one. This program is like the WRF model right there. So that's it. Maybe for a second, we'll jump to a terminal window and just say, right, so that's what we've got. We've got the WPS repository, we've got the MPAS tools repository, we've got the MPAS model repository, the MPAS limited area repository. And I went ahead and from the mesh download page, I've downloaded a couple of things. So I've downloaded a variable resolution mesh that we'll be working with, and that is this, where is it at? This mesh right here, this 60 to 3 kilometer mesh. So we'll be working with that for the first regional simulation that we're going to set up. But as we said, when you download these meshes, the refinement is at the origin. Hence, you probably want to rotate that somewhere else. And the second static file that you can't download yet, but that you will be able to download by next Friday, is for this 15 kilometer quasi-uniform mesh. So this is a mesh with 2.6 million grid cells. And I point out the number of grid cells because we have this funny naming convention for our meshes that we call them something by the refinement factor. So X1 is a quasi-uniform mesh, X20 refines by a factor of 20, and then the number of cells. Maybe that's not the most descriptive thing we could have done, but that allows you to distinguish yourself from new users because you'll have these numbers memorized. You'll say, all right, the 835.586 mesh, and your colleagues will know what you're talking about, and you'll say, that's right, we're both in the know. And I've downloaded some GFS data as well. Every 3 hours. In retrospect, I probably should have done it every 6 hours just to make things go by more quickly. And I've compiled everything because compiling is pretty easy and it's rather boring. And I've already run the WPS to create these intermediate files from our quarter degree GFS data. So that's kind of our starting point in the terminal window here. And so maybe back to the flowchart for just a minute, and then we'll get into a terminal and we'll actually run some things. Okay, so we talked about repositories. I showed you that. Sorry, this is my reminder to jump to a terminal, otherwise I'll keep talking. So as I just showed you in the terminal, again, you can't generate your own meshes, but we've downloaded a couple of either mesh or static files. So that step is done. The first simulation that we'll run will be a variable resolution regional simulation. So the first thing that we want to do is to run this, this grid rotate tool to take that 3 kilometer region from the origin, and let's say we'll run a simulation over Colorado. Why not? So the idea is we need to apply some sort of solid body rotation, and that's done with this MPAS or this grid rotate tool. So the idea is simple. What we specify in a name list for this tool is some point on the original mesh, and it's easier to think of that as the center point of the refinement region. And we specify a center point where we'd like to rotate that point to along a great circle arc from the original point to the new point. And then in principle, what we can specify then is a rotation about the center point of that refinement region. That doesn't make so much sense when it's a circular region, because rotating a circle about its center gives you a circle that looks much the same. But for elliptical refinement, that allows you to change the orientation of an elliptical refinement region, for example. So that's kind of the general idea. So let's jump into a terminal and give that a try. So one of the values of you being here this morning is you get to see something that I don't think most people know about because we haven't widely advertised it. And we haven't advertised it because it's not quite, I think, in an ideal state right now, but there is a script that we have that sets up a run directory for you. And I think maybe we want to try to align with CESM terminology because, as you've heard throughout this workshop, you know, there's I think a close connection between MPAS and CESM and CAM. We can run as a die-core in CAM. MPAS is a major component of SEMA, et cetera. So we want to try to maybe unify terminology. So the idea is that you can set up a kind of a case directory with MPAS. And apologies, Brian, this is nowhere as good as the scene case control system, but we're getting there. We're getting SEMA-fied. We're getting seamed up. So anyway, I digress. The idea is, historically, we've said, oh, just change to your MPAS model repository and run everything there in the model repository, which is a terrible idea. So we're trying to move towards this idea that wouldn't it be better if you set up a separate directory where you're doing your different runs for a given case. So we have kind of a work in progress shell script that creates these run directories for us. So we can say MPAS model, testing and setup atmosphere, setup run dir. And I think we'll probably rename this at some point to like setup case directory or something like that. But the idea is you need to link in name lists and stream files and all of these things into a directory, and it's easier to do that with a shell script. So let's create a case directory, a run directory called something like 3km Colorado or something like that. So now we have this 3 kilometer Colorado directory, and it has a whole lot of things. But these lookup tables for all of the physics schemes, this is nothing that you wouldn't see in like the test EM real directory or the run directory in WRF. The important things are that we've got the atmosphere model executable, which is kind of like WRF.exe itself. We have this init atmosphere model program, and we have different name list files for the atmosphere model program, for the init atmosphere model program, and then we have these stream configuration files. But the point here is that we want to take that x20.535.584 mesh and rotate it so that we've got that 3 kilometer region over Colorado. So we can go into this MPAS tools directory and then go into mesh tools, grid rotate. And this is all described in that full slide deck for which we had a QR code. And the idea is that there's just a name list here where we can describe that rotation, right? So that's weird. Cut off. Try that again. Right in a different terminal window. This is not MPAS-A's fault. Otherwise, I'll try. Okay, yeah, so somehow I messed up the terminal settings in that other window. So we'll edit files in this one. Again, not MPAS-A's fault. But the idea is that we need to specify the latitude and longitude of some point in the original mesh. And this conveniently defaults to 0 because that's where the refinement is in all of the variable resolution meshes that you define. But now we need to specify the latitude and longitude to which we want to rotate the origin. So we'll just change that to maybe 39 latitude and let's call it 105 west longitude. And again, this config bird's eye rotation counterclockwise degrees allows you to rotate the orientation of the mesh about that center point, but it's a circle, so we'll just keep that as 0. So that's the idea. Basically, in WRF terms, this is basically like specifying your reference latitude, reference longitude for your course domain. All right, so we can save that, and then we can say grid rotate, lots of dots, mesh is x20. So we give the name of the input mesh that we want to rotate, and then we give it an output name. So maybe we can write this to our 3-kilometer Colorado directory. And let's call it something like colorado.global.grid.nc, just to remind ourselves that, yeah, we've rotated the refinement over Colorado, but it is still a global mesh. Again, this is completely up to you. But as we said, effectively, we're not changing the connectivity of any of the cells. All we're doing effectively in principle is just recalculating the latitudes and longitudes of all of the cells. So as you would anticipate, that's a fairly fast operation. And so now we have this colorado.global.grid.nc, which is exactly the same size as this X20 mesh, but all the latitudes and longitudes have been rotated differently. And we won't try to visualize it. I'll point that out at the end. The visualization right now is, I think, one of the major weak points of MPAS. And I think we mentioned that yesterday, that anyone who wants to help us out with better visualization tools, that help would be very much appreciated. But we'll just trust now that things are happening. So at any rate, we've got this colorado.global.grid.nc file. So we'll jump back to some slides here for just a couple of minutes. Okay, so the next thing that we want to do, rather than interpolating the static fields to the entire globe, we're going to take this other pathway here, and we're going to cut out some region that covers something like Colorado from that rotated grid. So we have this this limited area tool, and maybe some of this text doesn't matter, but there are essentially different sorts of regions that you can define with this tool and extract. So we'll go through these in a couple of slides. The simplest thing that you can do is to just extract a circular region from a mesh. And that's fairly easy to specify, right? So you give it a name, you say that the type of this region is a circle. This point is just the latitude and longitude at the center of our circular region. And then the radius is the radius in meters of the circular region, right? So it couldn't be easier than that. You don't have to think about map projections. You don't have to think about true latitudes. You don't have to think about EWE and ESN values. You don't even have to specify delta X and delta Y. You simply specify the center point and how big your domain is in radius, and that's it. So point number one, easier than running GeoGrid. Okay, so the next thing that you might want to do is to cut out an elliptical region. So here things are a bit more difficult. So again, the center point of the ellipse, the length of the semi-major axis, again in meters, semi-minor axis, and then this orientation angle, which tells you how the semi-major axis is rotated off of a constant longitude line. Don't remember it. I hope it's counterclockwise as positive. If not, we should change that because that would be the proper thing to do. Now, this one is a bit different. It in essence has two boundaries, so it's topologically different, right? We've got a southern boundary and a northern boundary. In other words, this is a domain with a hole in it. So you could do crazy things, right? So this is a channel domain with an upper bounding latitude and a lower bounding latitude, but you could be really clever, right? So this is one of the nice things about MPAS is you can get creative with these unstructured meshes. So what if we were to set the upper bounding latitude to right about here and the lower bounding latitude to the equator? So now we've got a domain with a hole in it. So we could cut out a region and then we could rotate that region so that we've got a hole over Colorado. So we could run a regional simulation that covers all of CONUS except for Colorado. You can do that, and I challenge all of you to try that. These are the sort of things that you can do with MPAS. I mean, maybe you shouldn't, but you can. And then lastly, kind of in the most general sense, you can say, well, I don't want a simple ellipse or a channel. I want something that avoids topography. So you could specify, we probably should have called this like polygon or something like that. Maybe we can make polygon as a synonym in this text file that you use to configure a region. But we need to specify firstly a point that defines the inside of the polygon, right? So if you had a polygon that covered the entire hemisphere, how do we know whether that polygon is the northern hemisphere or the southern hemisphere? We need to say this point defines inside the polygon. So if we set this point to like somewhere out here, our domain would be everything except for Australia. So again, you could do that, absolutely. And then we specify the latitudes and longitudes in counterclockwise order of all of the points that define this polygon. And you can click around in Google Earth and get all of these points, and it's really painful, but you can do it. So that's effectively it. The last thing that I'll say that is maybe a little bit more difficult right now with MPAS, global, but also regional MPAS, is that if you run WRF, you never have to think about mesh partitioning. You just say MPI exec-N32, and WRF knows how to partition your rectangular domain into 8x4, tiles or something like that. In MPAS, because we're working on an unstructured mesh, after you extract a regional subset, we have a connectivity graph of, in this case, Australia, but we need to partition that limited area mesh across some number of partitions. And we do that with this tool called MPAS. So we'll talk about how to run that in the terminal here. So we've got this Colorado rotated grid, but it's still global. So we want to use this limited area tool to cut out a subset of this. So we can go to the MPAS-limited area directory. And so all of those text files for defining different sorts of regions are in this docs something directory. And maybe we should have just called them like, polygon, circle, ellipse, channel or something. But I think for some reason we called them names that were based on where the regions were located, which is completely irrelevant when you're just trying to see an example of a polygon. But at any rate, we'll try to run a circular domain over Colorado. So maybe as an example, we'll copy docs, points examples. Which of these is a circle? India.circle to, we'll just call it like region.pts. It doesn't even have to be called PTS, which I think was points. So the idea is that we give this a name, and this is the name that the regional mesh will be named. So let's call this something like Colorado, spelled the correct way. Maybe we'll center this again where we centered our variable resolution mesh. It doesn't have to be, but why not? And maybe as a radius, instead of 2,000 meters, let's try something like 600 meters. And let's do this. So the way that this works is we just say create region. And then, because you're here, you know something that everyone else doesn't know. On Wednesday, I hacked in a little capability, and we'll make a pull request for this probably early next week. But we hacked in a capability to say -- plot. And so it uses Cartopy and matplotlib to plot the region that you've specified in that file. So this is kind of similar to what you would get with the plotgrids.ncl script, if any of you are familiar with that. So we realized, so like these demonstrations are always, that it puts pressure on us as developers to say, I can't tell people like, oh, you have no way of visualizing your domain. So you quickly write some code. So you can say -- plot at any rate, the name of the region definition file. And then because this is hacked, but we'll clean it up before we actually commit this to the repository, you still have to give it the name of the global mesh that you're going to be cutting out the region for. You shouldn't have to do that when plotting, but you do right now because this is hack. So we'll say meshes, no, 3 kilometers. So we're trying to cut out a subset of our colorado.global.grid.nc file. So we run this, and I'm in the wrong terminal to do that. So let's try it again over here. Thought of a clever thing I could have done. Let's try to copy. Sorry, I've got two terminal windows. One is on a batch node of Cheyenne, so that I don't get in trouble for running things on the login node. So on Cheyenne, we've got a special Conda environment that allows us to use Car2Pi and things like that. So that's why it didn't work. Again, not MPAS's fault. So that creates a PNG image right now. So we can just say like display region dot in our messed up terminal. Hey, see, there's our domain. Let's try that again. In the other terminal window, not MPAS's fault. So you could kind of see, once I learn how to use Car2Pi and draw like state boundaries, this would be a lot more useful. But again, this was like Wednesday, during a coffee break sort of thing. But the idea is you could see how you could iterate on this, right? You could say, all right, now I can make out something about the Rocky Mountains here. I want to shift my circle domain eastward. If it was an ellipse, I want to change the orientation of the ellipse. So you could see how you could iterate fairly quickly with this plot capability, which again, we'll fix up. But that's the idea with that. So after we said, okay, yeah, I'm pretty happy. Oh man, I wish I didn't have such a messed up terminal window. And we're going to say without plotting. Sorry about that. So the idea is, all right, we've got the domain where we want, so we're going to omit that -- plot option. So we're just going to say create region, the name of the text file that describes the region, which again is just a circular region, and then the name of the typically global grid that we want to subset. So we just run that. The first thing that happens is we actually, even in the case of a circle, we define a set of points that approximate a circle. So everything reduces to a polygon internally, and we need to go through the global mesh and find pathways in the mesh that connect all of those circular boundary points. We're creating all of it. We shouldn't have called these boundary layers because boundary layer means probably something else to all of you. These are setting up, building out the relaxation zone layers and the specified zone layers. And then we fill in and identify all of the cells in that unstructured global mesh that define inside of our region. And then we go through and basically just extract all of those cells and re-index them. So that means like in the global mesh, cell number 42 had a certain set of cell neighbors, but some of those neighbors might be missing. So now we need to re-index everything to a contiguous range of cell and edge and vertex indices. So that happens, and we subset the file. And now we have our regional file. So if you look at the file size, trust me, it is about several times smaller. And we also have this graph.info file. So this is that connectivity graph of all of the cells in our regional mesh. So let's move these to our case directory. Right, if the terminal is working, like I really feel like that should have worked. All right, so we've got our global grid, and then we've got the regional grid just with that circular domain over Colorado. So while we're at it, we might as well partition that graph into a couple of different numbers of partitions. When we run the model in parallel, we need one of these graph partition files. And we do this with a tool called MPAS, which is fairly easy to install. And I should point out that you say this is a step that we didn't have to do in WRF. And in principle, we could do this partitioning online. And in future, that might be a capability that you just run MPAS, and online it partitions the graph, whether it's regional or global, calling MPAS as a library. But at any rate, we can say GP MPAS dash. Wish I could really read what was going on in this terminal. Oh gosh, sorry, I need to fix this terminal. This is driving me insane. that the problem? No. It's really, really maddening. And you have to like guess what characters you did or did not type, right? So this is a long command and you say, couldn't we provide a wrapper script for this given that these options don't generally change? And the answer is definitely yes. So we're going to partition this mesh twice, once into 4 partitions and once into 36 partitions. You can see how fast that is. So there's not really a good reason for not doing that online, other than at the time, I think we just didn't want there to be more library dependencies for compiling MPAS. The idea was as few dependencies as possible. But given that you have to install MPAS as a command line tool anyway, why not just install it as a library and link with it? It's probably, you know, we've over time you start to see the error in your past decisions, right? And that's true here as well. So anyway, back to the slides. So we have back to the slides. Anyway, we've partitioned our regional mesh. Now, the next thing that we want to do using this init-atmosphere model program is to interpolate static fields onto that regional mesh with refinement over Colorado. So we do this again with this init-atmosphere model program. There's a few input files and there's a common pattern here, but there's a few input files that we need to set up. So there's this name list file where we'll set a few options. There's the streams file, which is something that you don't have in WRF, but we'll see what that's all about. And then as input, we need some regional grid file. This happens to be refinement over the Arctic, but you can imagine that this would be the same thing with refinement over Colorado and its variable resolution. As output, we get a log file, and the end result should be this static file. So this is kind of the equivalent of a goem.d01.nc file. So we'll jump back to the terminal now, and we'll try that. So we're in our run directory, and we've got this init-atmosphere model program. And so let's go in and let's edit this name list file. All right, we're not going to edit in this terminal. By the way, if anyone knows what's going on with this terminal, please feel free to shout out and say, Michael, run this command to fix. Yeah. Thank you, Lee. Yeah. All right. That's awesome. Thank you, Lee Orff. This is crowdsourcing a demonstration. Yes, that's awesome. That literally made my day. All right. So there's a couple of different philosophies here. Given that we're going to be running the init-atmosphere model program several times, the first philosophy is why not go through and make every change that you can to the name list first and then never have to edit it again. The other philosophy is just change what you need for a particular step, in this case, interpolating static fields like terrain and land use onto our regional grid. Here, maybe we'll just try to edit a lot of things at once, but I'll point out which step those are relevant to. So this init case 7, we've always intended to give these names, but case number 7 is the case for creating real data initial conditions, including the interpolation of static fields. So we'll keep this as 7. Just like when running GeoGrid, the dates in your shared name list record in the namelist.wps file they don't matter. That's the same here for static field preprocessing. But since we're already editing the file, we might as well set these to the start time for our regional simulation and the end time. I downloaded GFS quarter degree files just for one day from the 19th through the 20th of June. So we'll set that. These options, we don't generally change, so we probably actually could just omit those and let them take on their default values. So I'm going to delete a few things to convince you that if we get rid of things that hardly anyone changes, the name list really is quite simple and it's not overwhelming at all. The number of vertical levels, the number of soil levels, these are things that only matter when we generate a vertical grid or interpolate initial conditions and lateral boundary conditions. So we don't need to set those now. This is the number of first guess levels. So this is basically num metgrid levels in your nameless.input file for the real program, and num first guess soil levels. In terms of data sources, we need to specify the path to those geographical data sets, just as you would do in your nameless.wps file with geog data root. Is that what we called it? Something like that. Config met prefix is the prefix of our intermediate files. So we'll change that to GFS. Again, this doesn't matter for static field preprocessing, but we're just going to go through and just change everything we can up front and then have to edit very few things after this. If you were creating an SST update file, we could use a different set of intermediate files for that, but we're not. This first guess interval, I think this is basically the same name without config. This is FG interval when running the metgrid program and the Rio program. So we'll set that to 10,800 seconds because we have these GFS intermediate files every 3 hours. These are choices of different data sets for static fields. This is kind of the equivalent in your nameless.wps file of setting geog data res, but I think we really discourage you from changing the defaults. So we could actually just delete those, delete that. Yeah, so that's a good question. Yeah. So the short answer is no. So for anyone online, the question is like in GeoGrid, you can overlay multiple sources of static fields. So you might say, I want to use MODIS land cover data set over most of my course domain, but then, for example, over just a small region, I want to use like high resolution land use or topography, or a land use data set that has certain other land use categories or something like that. Right now, that's not possible in MPAS. I think if there's a big enough push and if we get to that point, we could certainly implement that capability. And at that point, I think we'd probably want something as flexible as like a GeoGrid table. We could call it like the MPAS table or something like that. So certainly in principle possible, but I think we've just not gotten to that point yet. Yeah, another question. Yeah, that's a good question. And again, for anyone who's tuned in online, the question is the set of meteorological files, these intermediate files here, do we assume that those are on constant pressure levels? And the answer is no. So we have absolutely initialized from like model level European center data and things of that nature. Yeah, so the same, I guess, the same requirements apply as for the metgrid and Rio programs. As long as you have a 3D geopotential height and pressure fields, you should be okay. So whether they're weird, isentropic levels or things like that, should be okay. So these, at the moment, we don't really recommend changing to other static data sets. So in principle, those could go away. When it comes to generating our 3D grid, this is where we would set the model top. Again, in our height coordinate, the upper boundary is a constant height surface at present. So this is in meters. Things about like how we want to smooth the terrain and the effective terrain that's seen by the vertical coordinate surfaces. We won't set this yet, but if I forget, please remind me to set this to true later. We'll talk about this terrain blending around the boundaries. We'll illustrate that in a few slides. Interpolation control, I think the default is good. So again, that could go away. And then for real data initial conditions, there are these pre-processing stages. So the key thing here is that we do want to interpolate static fields. We do want to compute the subgrid scale orography fields that are needed by the YSU gravity wave drag scheme on the native MPAS mesh directly from 30 arcsecond topography data. So we'll set that to true, but we'll change all of these other stages to false. And then here, if we run in parallel, we do need to specify the name of that partition file. So that would be something like colorado.graph.info.part. So if we simplify the name list, it's not all that daunting at all. And all of these nameless options make sense. So let's save changes there. The other thing we have to do is to go into the streams.init-atmosphere file. And there's a whole lot of streams here, but the only ones that matter for our purposes are just this input stream, which is named input, but it's also an input stream. So we need to give this the name of the regional grid file that we want to interpolate the static fields onto. So our input is the grid file, which I think we called colorado.grid.nc. And the output should be the static file. So let's just call that colorado.static.nc. And the rest of the streams don't matter yet. So we'll just ignore them. So the full tutorial kind of gives some motivation for why we have this apparently overly complicated XML file for setting the names of input and output files. But for now, just know, if you're new to MPAS, that basically you specify the name of the file that we're reading in, the name of the file that we want to ultimately create, and that's it. So now we can run in parallel the static field preprocessing. And let's give that a try and see if it works. So in that run directory in another terminal, so it's reading in the input file. It's actually taking a little bit more time than I would have guessed. Okay, so this is going to be the longest 131 seconds of the entire morning. So what's happening basically, I can talk while this is running, we're going through and we're interpolating the 30 arcsecond GMTED 2010 data set just onto our Colorado domain. And the idea is that we'll go through and do this for the terrain, the soil categories, land use categories, climatological monthly albedos, vegetation fractions, and so on. And so you might wonder, why are we doing this just on 4 processors? Why not use 36 processors, which is how many cores we have available on one of the nodes of our computing cluster here? When it comes to the nameless.input file, so we have also activated the computation of these subgrid scale orography fields. And this is a bit of a work in progress parallelizing this, but right now, every MPI task for this step reads in the global 30 arcsecond data set, which is about 3.7 gigabytes. So if we fully subscribe the node, we'd have 36 MPI tasks, each allocating 3.7 gigabytes, which would blow out the amount of memory that we've got on a batch node. So when this stage is set to true, generally, you may find that you need to undersubscribe nodes just to make sure that you don't run out of memory. So this is something that's a work in progress. And I think as we become more clever and as we get through our backlog of other things, this is something that we'll parallelize in a better way so that we only have to read in the 30 arcsecond topography just over Colorado in order to compute subgrid scale variance, asymmetry, length scales, convexity. So that, I hope, explains why we're only using 4 MPI tasks right now for this. All right, so now we've moved on to the soil type. And this will run for a few more minutes. So maybe while this is running, are there any questions at this point?
Oh, well, I have a dumb as dirt question. There's just kind of clarifying. When we specify the radius of the domain we want to cut out, is that the radius? How are we looking at the radius? Is it the projection of that part on a plane, or is that some other kind of metric we're talking about?
Yeah, no, absolutely a good question. So when we cut out our circular region in the, where was that? The MPAS limited area, I think we called it like region.pts file. This radius here is a great circle arc distance. So I guess the key thing to emphasize here is that these regional MPAS domains are not domains on a plane. They're actually subsections of the surface of the sphere. So all of the distances are great circle arc distances, and all of the areas are like spherical areas, spherical shell areas. So excellent question. All right, still running. All right, so now we're on to the max snow albedo field.
Michael, can you entertain us?
Of course, I would welcome some distraction from staring at the screen, yes. Sorry, was there a question? Okay. You know, MPAS tries to give you an opportunity to go get a cup of tea or coffee as you're running it. So that's one of the nice things. So I guess, is the question ready? Otherwise, I've got a few more things I can say to fill up time.
I have a question.
The question, sorry,
Go ahead.
the question is the in custom grid, the center should be centroid, the centroid? In custom grid, the center should be the centroid? That's just.
I think I understand the question, right? So yeah, this will be easier if we jump back to the slides here. So I think the question is, like, right, for this sort of region type, we need to specify a point that defines what it means to be inside the polygon versus outside. This doesn't have to be the center. Yeah, it's so we kind of do kind of like a flood fill, right? So if we can mark all of the boundary cells, the cells that form the perimeter of this region, and we take any point, find its nearest cell or the cell that contains it, and then do like a flood fill out from there. That's basically what's happening. So as long as it's properly inside this region, you should be totally fine.
So I was one of those people who failed a couple of years ago to get PIO working. I'm just curious which IO you're using for your demo.
Oh, excellent point. So the log files try to be as helpful as they can, right? So if we look at the log file here, this is something a bit new in version 8. It tells you which version of MPAS you're running. We also have found it useful to output the result of git describe -- dirty. So you can see I've made local modifications. I'll tell you what those are in a minute. But this is useful when doing development and also when doing user support, right? If someone says, you know, MPAS is failing, and we say, oh, that's really amazing, it should not be failing. And we say, wait a minute, you've modified something. It says dirty there. What did you actually modify? Run git status. But to get to your point, we print out some compile time options here. And one of those is the IO layer. So I've compiled and I'm using the new SMEAL IO layer for all of this because I thought, right, if we're advertising this as a great new thing, and it would be kind of bad if we're like, but we're not actually going to use it because we're not confident in it. So yeah, we are absolutely using SMEAL here. But it also tells you other things like which build target we used when compiling the code. Again, this is useful from a support perspective to say, oh, well, I already know you're using the Intel compilers because you compiled it with the iFort build target, whether you used, that was weird, OpenMP or OpenACC, whether it was single or double precision, whether it was a debug or optimized build. Actually, if you browse the forum, you'll see that there was a recent question about MPAS running really slowly using an old version before we included this in the log file. And it turns out it was a debug build, and that's why it was so slow. But had they been running MPAS version 8, we would have seen compiler flags debug and been immediately able to offer some better advice. MPI task count. Did I not say MPI exec -N4? Maybe that's why this is running so slowly. My goodness. Yeah. Now I'm really. Oh, maybe I'm in a different directory. No, I'm not. That's really weird. Oh, also, yeah, the fact that it says task 0 of 1, that's disconcerting. All right, well, we'll see how this goes. Oh, maybe it finished. Also, I don't remember seeing this attaching 6.0 something to that message before, which is kind of weird. Otherwise, I might try to get another batch node here if this doesn't work out. Yeah. Yeah, I was thinking, I was like, this is the longest, it should take about 2 minutes. So yeah, all of the things that happen when you try to do things live.
Can I ask a question?
Yes, please, absolutely.
FV3 limited error model configuration. For the grids, we set up the lower left corner and then the delta X. Is that better achieved in the custom category in your grid? Like set up the 4 corners, flat and long?
Yeah, so you can absolutely do those, and it's easy to do in terms of setting up a region just in terms of bounding latitudes and bounding longitudes. And I guess I could say if your aim is to match an existing WRF domain, you might know that inside of the geo.em.v01 file, there's a global attribute called like corner latitudes and corner longitudes, or maybe corner lats and corner lons. So you could get those exact latitudes and longitudes. And I think where your MPAS domain would differ from the WRF domain is that we connect those corner points with a great circle arc or something kind of approximating it. And in WRF, it would be a straight line on some projection, and those lines might not be the same on the Earth's surface. So it might be a little bit challenging to exactly match a WRF domain, short of getting the latitudes and longitudes of every one of the bounding rows and columns of the WRF domain and using those as a polygon. But you can get a close approximation to it.
Another question I have is for the current case, you set up for the Colorado grid. So it basically still do the global simulation, right? And then move to Colorado and move to a higher resolution run.
Yeah, so the idea here is that we've taken a global grid that refines from 60 to 3 kilometer resolution. We've rotated the refinement over Colorado, so it's still a global grid. But then when we ran that limited area tool, that cut out just that circular region that was in blue. So all of the other cells are now gone from the mesh.
Oh.
So I can actually illustrate that here. So if we say like ncdump-h colorado.global.grid.nc, you'll see that this has 835, 586 cells in it. But if we say colorado.grid.nc, which is our regional subset, you see that it just has 139,000 cells in it. And so that's the mesh on which we're interpolating the static fields. Apparently not in parallel, but we'll try to figure that out. So from that point onward, everything is just a regional mesh.
Okay, so maybe you will mention this later. So is it possible to do 3 kilometer and then moving to 1 kilometer? Is that similar to nested domain? But I understand this is a variable resolution.
Yeah, absolutely. So you can get kind of the thing that probably nesting is a poor approximation of, which is taking and having coarse resolution along the boundaries of your mesh, maybe something that matches the resolution of the driving data set, and then slowly refining as you get to the interior of the domain. So all in a single continuous mesh with MPAS.
It's doable. Yeah.
Yeah, absolutely doable.
Hi again. I have a pedagogical question and something about how you're handling the model levels. The levels in the source data. So first up, are there any? Do we have a really basic minimum frills name list available on the website? Because if I want my students to use this, they're going to get confused by all these extra options, and they don't know what is needed and what isn't, right? So.
Yeah, I guess there isn't really at the moment. The closest thing that we have, there is, I think on the MPAS download page, there's something that says test input data sets for real data simulations. And maybe we can try to clean those up a little bit to make that this is the minimal possible thing, and maybe even add comments to the name list, some annotations that try to say, only applies if this or something. So I'd be happy to kind of work with you to find something that we think, this is really great for students or pedagogy. Yeah.
Great. And I have a technical question about how the med-grid replacement system here works. So you mentioned that I forgot the name of the program, but when you mentioned that MPAS, maybe init atmosphere model, is able to take in ECMWF pressure levels or model level data, or even height level data from some other source. So is there how is this controlled? Do we need to like adjust some kind of V table or and the code just detects it on its own as long as there are like certain variable names inside the file?
Right, yeah, so it's that latter. The variable names are significant. So I think like when we get to the creation of initial conditions, we'll see a list of the variables. And so we look for something called, I think PRES, or maybe it's pressure all spelled out. And if we find that, then we say, I don't know, it's probably a general vertical coordinate. But if we don't find that, then we assume, if you've ever looked at the headers of those intermediate files, the records in the files, they contain a level. And we assume if we don't find a 3D pressure field, that level value is the isobaric level value.
Okay, so guys, so basically this depends on ungrip and the ungrip V table to parse the original data source first, and then,
Mhm.
okay, got it. Thank
Yeah,
you.
absolutely.
Hi, Michael,
Yeah.
right here. I was just curious about halos, and I noticed in your Australia domain you had it cut out, but it was all on a uniform grid. So is there a built-in halo for that, where you're transitioning from your global to your regional?
Yes, so good question. So what we do is, unfortunately, I threw all the slides out from the presentation, but if you go to the full slide deck, that first QR code, effectively, we cut out all of the cells that lie exactly in the region that you've defined. But then, because at that point, we still have the global mesh, we build layers outwards for the relaxation zone and specified zone layers. And those layers are in grid point space. So what you'll find is if the boundaries of your mesh are on the 60-kilometer part of the mesh, you get 7 layers of 60-kilometer cells versus 7 layers of 3-kilometer cells if your boundaries were inner. So it's just building out layers in grid point space. Yeah. So because I'm really doubtful that this actually ran in parallel, at least based on the log file, and the fact that we got that weird message, I'm just going to log out here for a second and start a new interactive session on a batch node. And hopefully it works this time. Probably all of my frantic trying to fix the terminal, I'm sure I screwed something up. But I really want things to run in parallel from here on out. So hopefully it doesn't take long to grab a node of Cheyenne. While that's happening, I think we can switch back to the slide deck for a second here. Right, so. All right, so now we've interpolated the static fields onto our regional grid, and that took longer than it should have because of Cheyenne reasons, again, not MPAS-A's fault. The next thing that in principle we want to do is to blend the high resolution terrain that we just interpolated with the terrain that's going to be used for our first guest data set. The idea is that we don't want to do vertical extrapolation of atmospheric fields along the boundary because that tends to lead to poor boundary conditions. What we'd like is for the terrain along the boundaries to exactly match the terrain in our driving data set. So that's what's happening with this terrain blending. Again, once we finalize the terrain field, we can build up these smoothed hybrid terrain following vertical coordinate surfaces. And then logically, not logically, the opposite of that, illogically, we combine that with the interpolation of these initial conditions. So when we get back to the terminal, we're going to run all of these steps at the same time, and we'll talk about how that works. But just a few words about this. Talking about static fields. Just a word about this terrain blending. So this is activated by this blend boundary terrain option. And I think that this could always just be set to true. The code is smart enough to detect that it's a global grid or a regional grid. And if it's a global grid, it doesn't try to blend the terrain along the boundaries. So there's almost no reason that this shouldn't just always be set to true and just not even be a nameless option. Just detect if there are boundaries, blend the terrain, otherwise don't. But I think for now, we've taken the approach of make everything an option until we're absolutely sure that I've never had to set it to anything other than the value that we ultimately will set it to be. The idea, again, as we just said, is that if we've got, say, a high resolution 3-kilometer regional domain that cuts through parts of the Rocky Mountains, this is the San Luis Valley. My hometown is right about here. If you're interested, so right on the boundary. I don't know why I didn't put my hometown like further inside the domain. And yet, if we're using initial conditions from the 1/4 degree GFS, this is the terrain as seen by the GFS. And you can see that there's quite a bit of a mismatch along the boundaries. And that would mean that we might have to, extrapolate downward in some of the valleys that are better resolved in our regional domain. And that leads to kind of like poor inflow conditions. So what we would like to do by setting that blend BDY terrain flag to true is before we generate the coordinate surfaces, which depend on the terrain, we want just in the relaxation zone and specified zone cells to do kind of a linear blend of the GFS terrain with our first shot at the terrain. So that's basically the end goal of all of that with that terrain blending step. When it comes to interpolating the initial conditions, again, the idea is that we've got this static file and online, we're going to blend the terrain. We're going to make some more changes to the name list, to the streams file. Now we need these intermediate GFS files because we actually need temperatures and humidities and winds and things like that for our model initial conditions. Out comes a log file and something that by convention is called something.init.nc. And that is the file that contains the full initial conditions for our regional simulation. So hopefully by this point, we've got a Cheyenne session. Let's just set up a whole bunch of modules here. All right, so let's go back into our 3-kilometer run directory and let's go back in and edit our nameless.init-atmosphere file. And so we've kind of gone through and set most of these things. So still setting up real data initial conditions. So still case 7. Now we actually need the start time. The ending time, the stopping time is only needed when processing multiple time periods for the LBCs. So we could actually set this to, garbage right now if we wanted, but let's not. Now here would be the point at which we could choose a different number of vertical levels and a different, for example, a different model top height. We've set most of these things and we've talked about them. But getting down here, the important part is that now we do not want to interpolate static fields again. We do not want to compute these subgrid scale orography fields. What we do want is to set up a vertical grid. Oh, sorry, you guys were supposed to remind me to set this to true. We do want to activate this, this terrain blending along the boundaries. So we'll set blend boundary terrain to true. We will set up a vertical grid. We will interpolate meteorological fields. And talking to Laura Fowler, this fractional sea ice option, we should probably just always set to true because most meteorological data sets these days do provide a fractional sea ice field. So we should probably just always set this to true. So that's it. We're just no longer doing static interpolation, but we are generating a vertical grid and interpolating meteorological fields. And that's it. So there's a value to doing everything up front, right? We changed like 2 or 3 things in our name list. We can already save that and quit. We can go into our streams.init-atmosphere file now. Now the input is going to be our static file because we need that terrain field. And the output is going to be maybe just by convention called init.nc. And that's it. So that was it. In like 30 seconds, we've edited a nameless file and a streams file. Now, because we're not doing things that require a lot of memory, we can run this hopefully with 36 MPI tasks. So let's try that. Oh, the fact that we've got multiple files is not good. And one of them is called error. Okay, so we've tried to be pretty good with our error messages in MPAS, right? So it says error opening file with terrain field, GFS, something, something, something. And this is to do with the terrain blending, right? So we need the first guess terrain, and that comes from the intermediate file, which probably should have been called GFS. So obviously, I forgot to link in the GFS intermediate files into our run directory. So you can infer this from much more reasonable error messages than you might get in other modeling systems. So let's link those into our run directory. It's a quirk of interactive sessions on batch nodes that jobs just don't die. So this is again not MPAS-A's fault. This is Cheyenne's fault. Oh, did it finally die? Oh, because I'm not on the right node. I'm sorry. Can't I select things, please? Yeah, you can do this. Again, not MPAS's fault, just a Cheyenne quirk. And I really, like, the trackpad does not allow me to double click on things. It's really annoying. All right. All right. Well, let's remove. So when MPAS does fail, whether it's the init atmosphere model program or the atmosphere model program, you get all of these error files, which you don't normally get. So that's maybe an improvement over WRF, right? We always say, oh, look at the rsl.error.0000 file. And new users say, why am I looking at the error file if I don't expect there to be errors? And you're like, I don't know, just do it because that's the way it is. In MPAS, you only get error files if there are actual errors, right? So that's an important thing. So let's remove all of those files. And let's try that again now that we've got our GFS files in our run directory. Probably already finished. You can ignore these. This is a requirement of the Fortran 2008 standard that when you hit a stop statement, it reports any floating point exceptions. IEEE normal is nothing to worry about. So again, not MPAS's fault. But the end result now is that we have a log file and no error files, and we have our colorado.init.nc file. So this is the model initial conditions. So jumping back to some slides, just very quickly. All right, so now we've interpolated initial conditions. The last thing that we want to do is to interpolate lateral boundary conditions, which looks almost exactly the same as initial conditions, except we do it at multiple time periods, and we only need a subset of the fields that we need in the initial conditions, right? For boundary conditions, we don't need soil temperatures and soil moistures and things like that. If you wanted to update those conflicting kind of with the NOAA LSM, you could do that through a surface input stream. So that's the only change there. In the interest of time, right, we've got all these steps and we can get back to a terminal. So let's go back in and edit our nameless.init atmosphere file again. It turns out, if you go through the full slide deck, that it's init case 9, which creates LBCs. We've set up basically every other thing here. So that's it. We just changed from init case 7 to init case 9. Oh, sorry, there was one other thing that we don't have to change, but we should change. It is important just to make sure that this first guess interval matches the interval at which you have your intermediate files, but we already set this to every 3 hours. But I just wanted to emphasize that, make sure that that interval works. And in our streams file, now the input needs to be something that has a vertical grid. So let's change this to init. And something that's annoying right now, but we will fix. 2 streams cannot have the same file name. So even though we're not writing out initial conditions, just change this to foo or something like that. We'll fix this in a future release. It knows that it's not writing out the output stream, which has initial conditions, but it does nothing about it right now. So annoying, but we'll fix it. So the input needs to be, again, our initial conditions, which have a vertical grid, and then just make sure that for this LBC output stream, that the output interval here matches the interval at which we're processing those lateral boundary conditions. And again, it's 3 hours, but you could change that to 6 hours or something else. But that's it. So we made just like a couple of quick changes. We'll rerun that. I know error files so far. So you'll see that it's grinding through all of the fields in those intermediate files, and it's processing them now at multiple time periods to produce these LBC files every 3 hours from those GFS intermediate files. And you can see that those LBC files are written as they're produced. So to answer someone's question from this morning, you could in principle now go and start running the model right now. And the model would read just the first 2 LBC times to calculate a tendency, and it would grind through time steps as you are producing LBCs, separately. So you could do that if you wanted to. So this should take just about a minute or 2 to grind through all of those 8 or 9 different GFS files. And while that's happening, because I want to get through a second regional simulation before we break here. Okay, now it comes to running the model. The idea is the same. The only difference from running a global simulation in MPAS is that we need to set apply LBCs to true to say, oh, by the way, model, you should actually try to read these LBC files and enforce lateral boundaries in the cells that are marked as boundary cells. So that literally is the only change you need to make in your model name list compared to running a global simulation. If you forget to do that, again, we're trying to be much better about providing useful error messages. So you get something that says boundary cells were found in the boundary mass cell field, but config apply LBCs was false. Please ensure that blah, blah, blah for limited area simulations. And hopefully that's a pretty readable error message. And you'll say, oh, right, of course, I need to set that name list option. The only other difference is that you just need to make sure in your model streams file that the LBC input stream has an interval that matches the interval of your LBC files. Again, otherwise you'll get a hopefully useful error message. And then when you run the model, you'll see periodically every 3 simulated hours a message that tells you, by the way, I'm updating the lateral boundary conditions, and they're now valid from sometime to sometime, 3 hours later, because we're updating them every 3 hours. So we'll see how that works back in a terminal window. All right, so we finished producing our LBC files. And so now we can go and edit the nameless.atmosphere file because we're going to be running the atmosphere model program, which again is the equivalent of the WRF.exe program. So we'll go through for config DT, the model time step, that same 5 or 6 delta X rule applies as in WRF. So for a 3-kilometer grid, we could probably go with an 18-second time step. The starting time was 2023-06. Sorry about that. 0619. Aren't time strings much nicer than start year, start month, start day, start hour, start minute, start seconds? Why didn't we do this all along? So you could specify 1 day, or you could specify it as 24 hours, or you could specify it as 1440 minutes. You can do whatever you want for the runtime. A lot of these options you don't necessarily have to change, so we can just let them take on their default values. The thing that we absolutely do need to set is apply LBCs to true. And then just like we did before, we need to specify the prefix of that mesh partition file, which was called colorado.graph.info.part.436, whatever. And then we could go down if we wanted, and we could say, oh, well, maybe we want to use a different physics suite. So let's use the convection permitting suite. Maybe let's call the radiation every 10 minutes because we're on a 3-kilometer mesh. And you can make other changes. But basically, those are the main ones: the time step, the start time, and how long you want to run for. And that's basically it. And apply LBCs to true. In our streams.atmosphere file, we need to set for the input stream the name of our initial conditions. So we'll set that to Colorado. You'd think I could spell that better these days. We could write out a restart file every day, but let's just say we want to write the restart files every 12 hours. This is kind of like the WRF out stream. So the default history stream, you can change the interval at which that's written. You could even change this to none if you say, I don't want to write out the history stream for some reason. And if you go through the full tutorial, you'll see how you can make your own streams that contain maybe just surface winds written every 5 minutes. That's super easy to do, and that's covered in the full set of tutorial slides. And a bunch of other things. Down at the bottom again, you just need to make sure that the interval for the LBC input stream matches. So we do that. So that's basically it. Now we can say MPI exec N36 atmosphere model. And all right, it didn't crash so far, so that's good. And so through the log file, again, you get the usual stuff. Telling you about the versions you're using. Okay, IO task count is 36, that's great. And actually, if we go back up again, it does say MPI task count is 36, so that's awesome. And then we get through a whole bunch of stuff that tells you about physics options. It kind of echoes back what it read from the streams configuration file, all the dimensions that it found. These are things that we put in because we found that we ended up asking people these questions all the time when trying to provide help. So we said, why don't we just put them in the log file, even down to how much memory is being allocated on this MPI task and across all MPI tasks. So that's kind of nice to know, like how much memory is this simulation actually taking? assuming that it didn't run out of memory and fail before it even got to this point. And then we get down to the actual model time steps, where we say, all right, the lateral boundary conditions are valid from the 19th at 0 UTC through the 19th at 3 UTC. And then we get to model time steps, each of which is summarized by the global min and max of the normal component of the horizontal velocity and the vertical velocities, and then the amount of like actual wall clock time that it took to take that time step. Right, so just like you do in WRF, you can look in the log file and say, all right, so we can simulate 18 seconds in about 3.6 seconds, ignoring radiation time steps. And you can say, all right, let's find out how much faster than real time we're running. How long is this 24-hour simulation going to take? So that's the idea. So that's it. And I think in the remaining 7 minutes, we can run a completely new regional simulation, but we'll do it fast just to really prove to you that it is easy. Let's kill this model job. Again, it's a weird quirk of the batch nodes of Cheyenne that MPI jobs just don't die with Control-C. So we'll do it that way. All right, so starting from the very beginning now, end to end, let's create a new run directory. The idea now is we'll do a 15-kilometer simulation over CONUS, but it'll be quasi-uniform resolution. So we can use that existing 15-kilometer static file. So we don't need to do the static processing because we have the global uniform 15-kilometer static file available in this meshes directory. So let's start by making ourselves a run directory. So we can say MPAS model testing and setup atmosphere. And what is the name of that script? Let's just call this like CONUS. So now we've got a CONUS case directory. So let's go to CONUS. All right, everything's good there. What's the first thing we should do? We should probably cut out a subset of the static file. So let's go to the MPAS dash. Let's go to the MPAS dash limited area tool to cut out a subset. Let's copy docs something. So we're creating just a region file. So we'll edit this file and we'll say, yeah, let's call this thing CONUS all caps. It's an ellipse. Let's center at maybe 39 degrees north and maybe minus 100-ish, 98. Maybe that's about the center of CONUS. Let's set the semi-major axis to, I don't know, about 4,000 kilometers. Maybe 1,500 kilometers. It turns out that, again, the semi-major axis is along a longitude line, but I'd like the ellipse to be rotated so that it captures most of CONUS. So let's change that to 90 degrees. And let's say create region dash plot CONUS and then meshes x1.2. So we'll make ourselves a plot just to make sure that I've not messed something up and gotten the longitudes like in the wrong hemisphere or something like that. So we get this PNG file, so we can say display region.png. Just make sure that this looks okay. So you say that doesn't look like an ellipse. It's because of the map projection. Trust me, it really is an ellipse on the actual the curved surface of the sphere. But when you look on it on whatever map projection I was learning how to use in Cartopy, it doesn't look very elliptical. But just trust me, it is an ellipse. If you do the same thing over the equator, or if you use a different map projection, you'll say, that's what I learned about in geometry in school. So trust me, it is. And you could see how we could iterate, but in the interest of time, let's just say that that's good, right? So now we say, all right, yep, no longer need to plot that. Let's just remove the plot option. And let's extract a region from the 15-kilometer static file to create a 15-kilometer CONUS static file. And this is probably the slowest part. But if anyone's keeping time, we started about 6 minutes to the hour with our completely new regional simulation. And I think we can maybe almost finish by 10 o'clock. So that's the point. In 6 minutes, end to end, you can run a complete regional simulation with MPAS. It is that easy. If only our code would just run faster. So this is all written in Python. The idea was, for students, wouldn't it be nice if students could go in and define their own region types or things like that, or hack on the code like I did on Wednesday? And it's, I think, an easier sell to tell a student, do this in Python, then, well, guess what? You have to learn Fortran before you can even change the way that regions are defined in MPAS. So that was kind of the argument. But if speed were an issue, maybe we could rewrite it in C++ or something that more students would know. Yeah, go ahead, Russ, first then.
Can you speak?
Yep, when you're creating your boundary layer, it shows 1, 2, 3, 4, 5, 6, 7, 8. You're doing it 8 cells deep here, is that correct?
It's 7. Where the 8 comes from, it turns out for vertices and edges, they have one more layer than the number of cells. So just like, an interval has 2 endpoints, 7 cells have 8 edges that form their boundaries, or 8 layers of edges. So that's where the 8 comes from.
Hi, I was just wondering, like, to make the Python, you may not need to rewrite the Python code into C or Fortran if you want to speed it up sufficiently. Maybe you could use just-in-time compile offered by Numba.
I was going to say, yeah, we could probably do some Numba stuff too.
Yeah, I mean, it looks like it's a bunch of for loops, right? That's the stuff that Numba is great for.
Yeah.
And another question, like, are there any, I mean, you have this like text files that control the streams right now, and it seems like you have to make multiple changes to them, which means there are multiple ways for errors to happen. So I was just wondering if there's like any plans to write a bash script that just SEDs and constructs new like stream files every like at different stages, so that people don't like put a comma in the wrong place.
So that's an excellent point. And this, just because I know there's at least one CESM person here, this is a bit of a different philosophy, is that we want to provide the basic building blocks and then allow others based on their use case to build layers of abstraction on top of that, rather than saying, you say create new case, and then if you want to change anything about it, it's a total black box and you're out of luck. The opposite approach is taken here. We provide the very foundations, and as you said, one could easily construct a script that says, time's up, interpolating static fields. But hey, if you guys stick around, if you're willing to defer coffee for like 5 minutes, we will get through this other regional simulation. The point is, yeah, you could easily build up these higher level scripts. All right, so now we've got our CONUS files. Let's move those to our CONUS run directory. Let's go to the CONUS run directory. Let's link in our intermediate files. Let's partition that graph file. Let's say gp metis -min-con. So we'll write a wrapper script for this. Let's edit our nameless.init-atmosphere file. All right, so creating initial conditions, we need to set the time to 2023. Type when I'm trying to speed up here. Never write code when you're in a hurry. We'll just use the default set of vertical levels. This prefix should be GFS, 10,800 seconds. We don't need to interpolate the static fields this time because that was already subset. We'll change this to we will just set the name of the input file to conus.static. And we'll call this, just in the interest of time, just init, because that's less stuff to type. All right, so we're creating our initial conditions right now. All right, done already. All right, let's edit that name list again. So yeah, we could definitely write a wrapper script for this that does like sed commands to change all of this around. So let's say that now the input is init. .nc. Again, we'll fix this. Sorry about this, but call that foo. 3 hours is good there. Actually, let's do this every 6 hours just to make this faster, right? So let's change this to case 9 to create LBCs. And now, yeah, just we'll update our boundaries every 6 hours, right? So this should take half as long. So we're interpolating the LBC files. They're already being written out. So as that's happening, let's go ahead and edit our nameless.atmosphere file. So for a CONUS run at 15 kilometers, again, using that 5 or 6 delta X rule, we'd use about a 90-second time step, 2023 06 19. Let's just do a short 6-hour run. Apply LBCs. True. Let's use the mesoscale reference suite, but let's call these every 15 minutes just for the radiation schemes. And then in our streams.atmosphere file, go through and set our initial conditions to init.nc. And now we need to read in our LBCs every 6 hours from the model. All right, we finished producing LBC files. Atmosphere model, again, just like WRF.exe, died already. Ooh, that was not good. Ooh, that's a failure. Ooh. Again, these jobs just don't die. Let's find out why. To prove to you that the log files are super useful. Could not open block decomposition file for 36 blocks. Did I not run Metis?
Oh, the name's wrong.
CONUS, right, okay. So, right, you say, why couldn't it open that file? The file's right there. And you're like, well, I must have spelled it wrongly. Right here. So let's change this to. I see, it didn't die this time. Okay, so it's reading the input file. Actually, it is running in parallel, right? Yeah, 36 MPI tasks. I suppose maybe IO performance is not so good at this moment. Maybe there's somebody who's grinding through some big data set this morning on Cheyenne, who can say. But anyway, the point is the model will, as soon as it finishes reading the initial conditions file, start taking time steps. So, okay, it took about 10 minutes, but in 10 minutes, if you know what you're doing, you can set up and run a complete regional simulation. Good grief, that is taking a long time. Not Smeal's fault. I blame Cheyenne again for this. But all right, so now we're to the point of taking time steps. So, you know, if you know what you're doing, and particularly if you're running a quasi-uniform regional simulation where you can just use existing global static files, in about 10 minutes, you can start up and run a simulation over CONUS or Colorado or Antarctica or whatever. So that's, I better stop there. And yeah, thanks very much for, yeah.
Now the most important question for me. So can we now open and display the output with NC view or use NCO or CDO?
So this is something, yeah, that's a really good question. And I forgot you reminded me that I did have like one other final slide that's worth showing here. But what's coming up? So you'll notice the last bullet point is improvements to visualization. So right now we have a couple of NCL scripts and some Python scripts that can visualize regional files, whether it's, you know, model output, model input, whatever, grids, but it's painfully slow to draw. There is NCView. So we have a tool called Convert MPAS, and this is described in the full tutorial material. So that was like that second QR code where we have a way of interpolating to a lat-long grid fairly quickly, and then you can use NCView. There's one glitch in the way that we remap some cells, so you get some interpolation artifacts right now, but we know how to fix it. And we have more software engineers now. We have more software engineers now trying to get their attention to help us out with this. It could, yeah, I guess, I don't know how actively developed NCView is these days, and we'd have to kind of get in touch with the NCView developer and convince them that they need to support our specific meshes. It is, yeah, you can download the source code. So yeah, we could make a fork of NCView or something like that. But it's much nicer to be able to make. Yeah, but you can. So in the interest of time, I won't, but you can, and it's described in the full data set. So that's this last bullet point here. So coming up, you might say, this is really good. You can subset existing meshes, but what happens if I want to run a 500-meter resolution or a 1 kilometer resolution MPAS regional simulation? That presumes we have a 500 kilometer or a 500-meter global mesh, which we don't. So that's kind of a showstopper. So we are working on a tool that will allow you to lay out as many columns and rows of perfect hexagons as you want at arbitrary resolution. Sorry, I keep talking. You guys probably want coffee. There's a few other things, feel free to ask me about them that are coming up. But the cool thing is you can produce initial and boundary conditions for regional MPAS from global MPAS. So this is kind of like end down, but for MPAS. So yeah, thank you.